queue, the ready queue, things like this. And now we're going to talk sort of about how do we decide what, how to actually perform the process of moving things around, what should be running, right? So for the rest of the week, again, I'm away. There are going to be 2 videos assigned. I'm going to try to, I don't know if I need to barnstorm through this stuff or not, but I might move a little quickly today. Hopefully I can get through this whole deck, and then you guys will just have sort of 2 full videos to watch as sort of homework for the rest of the week while I'm gone. And then on Wednesday, we're going to do design review in class. So please bring your designs, even if it's just the sort of rough outline of a design, at least have read the assignment. Come to class with some idea about how to do it, and we're going to sort of pair you up with some other groups so you guys will have a chance to talk about this together, right? Also, please, this is the week where you should be starting assignment 2, right? And recitations are going to move on to assignment 2 so that we can have enough time to cover the material you'll need to know for assignment 2. Hopefully, Wednesday's design document class will provide a sort of a good forcing function for you guys to get going on this. The last thing I would suggest, and I'm sure that whoever, I think it's Jinghao this week who's doing recitations, we'll talk about this on Tuesday, but the parts of assignment 1 that you're going to need to work are your locks and condition variables. Once those are done, you can start with assignment 2, okay? The reader-writer locks are fun, and hopefully people are sort of enjoying implementing them and trying to get them to work. The synchronization problems are completely unnecessary, and not doing them will cause you to lose points for assignment 1, but won't affect the operation of your system later. Yeah?
If you score 10 out of 10 points with the patch, it means they're working properly?
If you score...
The CV and the locks?
Yeah. Well, OK, let's put it that way. If you get 10 out of 10, it means that you got 10 points out of 10 points, right? It means that the auto grader couldn't find anything wrong with your locks or CVs, OK? That's not necessarily an ironclad proof that they are perfect and or working properly, OK? We do try to test a lot of corner cases. In fact, a couple years ago, I wrote a new CV test to try to test a certain corner case that wasn't getting tested by the other testing suite. The best thing to do is to have come into office hours and have one of the TAs just look over your locks and condition variables to make sure they look right, right? It'll take them a minute or 2 just to glance at them in order to make sure that they're doing the right thing. And if they are, then you can move on. Yeah. But yeah, I don't want to promise anything about what the autograder output means, right? It means you've got full credits. You should feel good about that, right? But I'm not going to say that it proves that your locks are correct, right? Good question. So yeah, but if you've gotten distracted by some of this other fun assignment 1 stuff, but your locks and CVs aren't done, finish the locks and CVs and then move on to assignment 2, right? If you have more time later, you can come back and work on the synchronization problems and get your whales to mate properly, right? But assignment 2 is worth more points than assignment 1, and it'll be a better sort of optimization of your own time to just keep going forward and backfill on this stuff later if you have time, okay? All right, so the first existential, we'll do the what, where, why, how about scheduling. So what is thread scheduling? Define thread scheduling. Yeah. Mm-hmm.
When the CPU would actually take the thread of the operating system would take the thread of the CPU and let another thread run.
No, that's not scheduling. What is that? What did he just define? That's a context switch. Okay? Scheduling requires performing context switches, but what is scheduling? Yeah, Matt. Yeah, deciding what to run on the thread. What to run on the CPU, right? Which thread should run. And that involves performing a context switch, but that is not the process. This is policy, right? So this is a choice. All the threads that are available on the CPU, which one should I run, right? This week, we're primarily going to talk about single-core scheduling, right? Multi-core scheduling, there are some interesting issues. However, to some degree, you can think of multi-core scheduling as multiple cores making scheduling decisions semi-independently, right? And I'm sure somebody watching this on the internet is going to give me a dislike on YouTube for saying that, because it's way more complicated than that, right? And there are research teams that have been working on this issue for years, right? And I just oversimplified it into one sentence. But we're going to talk about single-core scheduling almost exclusively, right? So why do I need to schedule threads? Why do I need to make this choice? So I know what scheduling is, Damien. Yeah. Some threads are just more important than others. I like that. Well, so that's something I might want to take into account when scheduling, but that's not why. Yeah.
The illusion of concurrency.
Yeah. Remember, what was the illusion of concurrency, right? What did the illusion of concurrency depend on? Why do I need to make this choice? What about there is something about your system that I could change that would make me not have to make this choice. What would that be? Yeah. Any ideas? Oh, I already called on Mac. Yeah.
Designing a system with multiple processors so all threads can run concurrently.
Yeah, I mean, I have more threads than I have cores to run the threads on, right? There's a scarcity here. I have a resource that I have to share. If I had 1 core per thread, I'd be in great shape, right? And you'd have a very, very fast system. But because I have fewer cores than threads, I have to make continuous decisions about how to schedule them. And the illusion of concurrency is something that will emerge from this process, right? If I do this well, the system will look like there's a lot more things happening at once that can actually be happening at once. If I do it poorly, it'll look like nothing is happening, right? And remember, and this is also your job as the kernel because you have this kernel privilege, right? So the other applications have allowed you to multiplex this resource, and their performance relies in large degree on how well the kernel makes these resource allocation decisions, right? All right, when do I have an opportunity to make this scheduling decision, right? So there's 3 or 4 cases where the kernel has to or creates an opportunity to stop one thread from running and run another thread. So what's one of them? Yeah.
Timer interrupt.
Yeah, so when a timer interrupt fires, right, that creates an interrupt which causes the kernel to run, right? And that's something that I use to implement what kind of scheduling? Preemptive, right? So remember, preemptive scheduling is this idea that I'm not going to wait for a thread to block, which gives me a natural chance to schedule something else. Instead, I'm going to force threads. I'm going to create these opportunities for me to make scheduling decisions periodically by generating these timer interrupts. But there are other times when I get a chance to schedule a new thread without using a timer interrupt. What will one of those be, James?
Syscalls?
Yeah, well, any sort of blocking system call, right? I can also call yield, right? So the most direct way I can create opportunity for make a scheduling decision is to call yield, right? Yield does not cause the thread to enter the blocked or waiting state. It simply tells the CPU, hey, you could, if you want to, right now, I'm creating the opportunity for you to make a scheduling decision, right? And you see, if you've looked at some of our test code, we use this to create more churn in the scheduler in order to make some of our tests more interesting, right? So if a thread makes a blocking system call, right, and the thread actually cannot continue executing, right? At that point, I need to make a scheduling decision. I have a CPU that's now available, or a core that's now available, and I need to put a thread on it. When the thread exits, clearly it's finished forever, and there's now a core available. And then this fourth option, which is when the kernel just decides that that thread has had enough CPU for right now. And as someone already pointed out, I implement this using timer interrupts, and this is what creates preemptive scheduling, right? So if I just relied on these top three options to gain a chance to run, that would be what's sometimes called cooperative scheduling, right? The kernel doesn't have a chance to schedule threads except for cases when threads do something that causes the kernel to run and gives the kernel the opportunity. And the fourth, by implementing timer interrupts, I'm taking that opportunity periodically. How well, I mean, with most applications, how well do you think cooperative scheduling would work? Well, I don't know. Why would you think it would not work very well? I mean, the question is, how often do one of these three things happen, right? Yield, probably not that often, right? Exit, not that often. But what about making blocking system calls? Happens a lot, right? I mean, applications that do stuff, right? that want to use the hardware, that want to like respond to user input, that want to use files, that want to use the network. I mean, they end up making a lot of blocking system calls. And in fact, remember, I don't even have to make a blocking system call. As long as I make a system call, remember, the kernel has a chance to run. And so even if I make a non-blocking system call, so these slides are wrong, right? It should say I can make either kind of system call, and the kernel now has a chance to execute. And if it wants to, it could just choose not to return from that call and to let somebody else run, right? We talked a little bit about this last time, so I'll just skip through it. I mean, yield is not something that's terribly important to understand, but it essentially gives, it forces the scheduler to run or allows the scheduler to run explicitly, right? And the only difference between yield and a lot of other times that the scheduler runs is that the thread that was running is not put on the waiting queue, right? It remains ready to run. It's sort of similar to a timer interrupt in that way, right? If I'm interrupted by a timer interrupt and I'm descheduled, that thread remains ready to run, and it can begin executing at any time when a core becomes available, right? So we've talked, and again, this is a nice, I want to sort of pause here and talk a little bit about the separation between policy and mechanism, because this is another, have we talked about this before? Remind me. OK, good. I have like about a 1-week memory at this point. So mechanism and policy, this is another sort of design principle that underlies a lot of good computer systems, and not just computer systems, but a lot of good computer software, right, including libraries and other interfaces, right? Which is to simply put, to separate the mechanism, namely how something gets done, from the policy embodied in making decisions about how that thing happens. So in this particular case, the mechanism that we've already discussed is, how do we actually switch between threads? Like, once I make a decision about which threads to switch between, what's the process of doing that called? I think you guys know this. You're just feeling shy today. It's a context switch, right? And we've talked essentially about the mechanism of scheduling primarily up to this point, right? We talked about how processors make it possible. That's the mechanism, right? That's what allows me to stop a thread and start another thread, right? Now, the second part of this, and quite isolated from the rest of this mechanism, is this thread scheduler, right? And the thread scheduler, in a nice way, has its logic quite not intertangled with the mechanism, right? So one thing frequently we try to do when we design computer systems is keep the policy and the mechanism separate, right? Give the policy some nice mechanisms to use to do what it needs to do, but allow those mechanisms to change, right? So, for example, the process of performing a context switch may vary between different processors. In fact, it probably varies a lot, right? Why would performing a context switch be something that would vary a lot between different processors? Yeah, Doug.
Different processors have different registers and how the architecture is set up between them?
Yeah, I mean, if I'm going to save the state of the CPU, I better have some understanding what that state is, right? And that state depends entirely on the exact details of what that microprocessor is and the specifications of which registers get saved, blah, 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 right? So there's a lot of sort of very low-level mechanism there. But the nice thing is if I make sure that that mechanism is all exposed via interfaces that are sort of appropriately designed, then the scheduler doesn't have to care, right? All the scheduler does is say, stop this thread, start another thread, right? And I can say that same thing on any system, whether it's an Intel processor, an ARM processor, whatever, right? And the details are not important to the scheduler who's making policy decisions. It just tells the underlying software, OK, I don't want that thread to run anymore. Okay, you figure out what to do to get that to happen, right? Yeah, OK, we talked about this, right? So let's go through another sort of example of this, right? So we already talked about that deciding which thread to run is an example of policy, and moving that thread off and on the CPU, as well as saving state about that thread, including where it is, running, ready, blocked, which is important information for the scheduler to know. These are examples of sort of mechanism, right? What about maintaining the running, ready, and waiting queues? Would that be a policy or a mechanism? Yeah, that's a mechanism. What about if I had a scheduler that tried to give priority to interactive tasks? It's a policy, right? In fact, someone I think last year realized you can tell based on where the colons are, but anyway. So the process of using a timer interrupt to stop a running task, that would be what? Mechanism. And then if I implemented my scheduler by choosing a thread to run at random, that would be an example of a what? Policy, right? And I mean, I think you guys have, most people have an sort of intuitive grasp of this difference, right? Policies make decisions about how things should happen, right? Whereas mechanisms implement those decisions, right? And mechanisms usually don't have a lot, deciding to build a house is an example of a policy, right? A hammer is a mechanism, right? A hammer doesn't know what it's building, it doesn't care, right? And the house, isn't going to get built without using some of these lower level mechanisms. All right. So scheduling is a particularly important part of how modern systems operate, right? And in fact, on Friday, or whenever Friday is for you, whenever you watch that lecture, you'll get to see sort of an example of how there's been sort of continued activity in the Linux scheduling world to try to continue to respond to changes in how devices are built and how people use them, right? Why is it so important why is CPU scheduling so critical to how the system operates? Yeah, Chris. The PCU?
CPU is where all the instructions for everything are carried out, so it impacts how our hardware regions are allocated.
Yeah, I like that answer. I want to make it more explicit, though. In other words, in order to gain access, so what does the CPU end up doing to the rest of the system? I mean, in order to use the disk, what do I have to do first? I have to use the CPU, right? I can't execute the code necessary to use the disk without using the CPU. Yeah?
If the CPU is not multi-blocked properly, it would create a bottleneck for everything else.
Right, so the CPU is a lot faster than the other parts of the system, right? And so if I'm not careful about how I allocate the CPU, it's possible that I can make the system look very slow, and I cannot expose the full power of the CPU to you, right? If I'm doing a good job of scheduling, maybe your CPU is busy a lot, right? And the system looks really responsive, and I'm doing a good job of maintaining the CPU. But it's also important to keep in mind that every other resource on the system is either something that's used while you're using the CPU, like memory, or is something that in order to gain access to, you have to use the CPU. So the CPU is the gatekeeper, right? I can't, take input from the touch screen without using the CPU, right? I mean, this all starts at the processor. And if I do intelligent scheduling, I can make even sort of an underpowered system seem quite responsive, and bad scheduling will make even a really, really powerful system seem really slow, right? So this has a pretty dramatic effect on how your system behaves. So when we talk about scheduling, I mean, one of the things that's fun when you start talking about thread scheduling is that there's a lot of competing objectives. And that's one of the things that makes this interesting, right? If this was a simple problem with like a simple design requirement, somebody would have solved it a long time ago. But it turns out that CPU scheduling is a very, very sort of complex problem because there's lots of different expectations we have about how our computers work, right? And when I started thinking about this, I sort of broke them down into 3 categories, right? And this one is actually a little bit new, right, to the way that computers have been used maybe in the last 10, 15 years, right? But this is my taxonomy. So there are 3 sort of things we expect computers to be able to do, right? One is we expect them to be able to respond to us, right? Sort of interactive use. So I call that, respond or click, right? When I click on something, I expect something to happen, right? When that breaks down, you guys notice pretty quickly. The second thing is, well, let me talk about the last thing. So the last thing is there are certain tasks that go on your machine that need to complete. They need to complete at some point, and you may not notice exactly when they complete, but they actually do need to finish at some point. And if they don't finish, you will notice, right? So this is sort of the opposite of click, right? This is not something that you see happen on demand, but it's these sort of critical functions of your machine that have to get done. The middle one is a little bit more interesting, and this I think has a lot to do with the use of computers as multimedia delivery devices, right? And there are some things where we expect computers to now be able to produce these sort of smooth streams of content, right? Whether it's audio or video or playing a computer game is another example of this, right? And this can involve meeting lots of sort of regular deadlines with a little bit of advance warning. Right? So responsiveness or click is this idea, when I touch it, it responds, right? And remember, I don't necessarily, it may not finish whatever I asked it to do. And some of this becomes a little bit more about API design than the actual function of the computer. But at least I want some indication that it understands what I asked it to do, right? It started, right? So I click on something, I get an icon, or I see that the button changed color, or the menu draws, or whatever, right? And a lot of what we do with computers, we expect this sort of responsiveness guarantee, right? You guys rely on this, right? So if I took one of your machines and I just added like a half-second delay for everything that you did, right, you become very frustrated, right? I mean, how many people have ever used a machine like that where it was almost, and it's almost like it starts to work against you because you open a menu and it doesn't seem like it's open and you click somewhere else and it turns out you've clicked inside the menu, right? And then some random thing starts happening that you didn't want to happen, right? So actually some of our actually my phone is like that now. I think smartphones have sort of gotten themselves stuck in this, right? Where it's like when it gets a little laggy, it just becomes very, very hard to use the interface, right? Because again, when you click on it, you're not sure whether or not that menu is actually going to come up, right? You wait for that split second that you're used to, and then you're like, huh, I wonder if it's broken, right? And then right when you think it is broken, it surprises you by showing up, right? So this timeliness is important, right? Because it drives sort of the way that we interact with the machine. And this is the process sort of using a computer, right? If you think about what makes computers different from television, at least if you're not the type of person who's like, constantly hitting the remote control buttons, this is kind of what computer use. So these are some examples of responsive tasks, but you guys know these, right? I mean, this is most of what you do with your machine, right? Any sort of web browsing, certainly editing, right? I mean, how difficult would it be to use an editor that the cursor didn't follow you quite, or like you were typing and suddenly there were keys that were missing, right? Yeah, that's a fun joke to play on people, actually. If you ever get hold of somebody's VNC terminal and you can just hit backspace from time to time while they're typing, that makes typing very exciting. And then chatting type applications, right? And chat's a good example of a case where when you hit send, right, you see the message as if it's sent. It's not clear that the person on the other end got it immediately, but you know that the message is in transit, right? So the interface is giving you some feedback saying this operation has begun, right? But that doesn't necessarily mean that the other person received it. It may be queued in some router somewhere, right? So continuity is this idea of asking your computer to do some continuous task and to do it smoothly, right? And continuity implies this sort of active waiting where you are actually still expecting something from the computer without interacting with it. So you start a video and you expect that video to play for 5 minutes, several hours with you watching it. And this, as computers have become essentially started to replace television and audio and have served sort of as delivery vehicles for all sorts of different sort of content, this has started to get increasingly important, right? So what about examples of a continuous task where you would expect the machine to sort of repeatedly perform some sort of not necessarily extremely taxing operation, but to do it at regular intervals? Yeah. Streaming of video. So video streaming is an interesting case, because I would argue that video streaming, at least in certain cases, can be a little bit computationally taxing, right? But that's a good example. What's another case where you're pretty sure that this particular activity is not like a big challenge for your machine? Yeah. Yeah, OK. So drawing the mouse pointer is interesting. There I'm actually interacting with the machine. So I would argue that falls more in the first category. What's another type of media? I mean, video is like lots of frames and it's fast and stuff like that. What's another type of media would be easier? Audio, right? I mean, our computers have gotten to the point where playing MP3 is just really not that hard, right? But if the computer decides to lie down for a few seconds and rest, and the buffers are queuing up, the buffer empties, and suddenly there's like a a hiccup or whatever, then you start to notice, right? The cursor blinking is another one of my favorite ones, right? I mean, it's funny if you think about it, but the cursor blinking is this form of sort of interactive feedback that, not really interactive, continuous feedback. I mean, would it be funny if maybe late at night this will happen to you actually when you're working on one of your OS 161 assignments. If you have blinking cursors set up, which you probably don't because I probably disabled them on purpose in your virtual machine because I hate them. But you imagine sitting there and watching the cursor blink and then it starts to speed up a little bit or like slow down. And, What is happening? But that's, and it's stupid, right? But you could imagine, like, if I'm not careful about how I do my scheduling, then there's some big background task that ramps up that's like indexing your entire file system, then, the blinking cursor could get a little bit out of whack. And then, of course, all these stupid web animations that the web is full of. Right? So the last category of tasks I just hinted at, but this is one where, this is one of the things that computers are fantastic at, right? One of the reasons why we keep them around is doing sort of things that take a long period of time, doing them in a way that doesn't interfere with us, but doing things that are useful and improve interactive experience, right? And you can think of these as sort of background tasks. A lot of times you guys aren't directly aware of these because they're not interactive tasks, and they're also not necessarily tasks that you initiate through an application, right? This is stuff that your system is doing sort of continuously to try to improve performance. What's an example of this? Can anyone give me one? Yeah.
While a software update is happening in the background, if you try to download any other thing, it says that the resource is currently being logged by some other person.
Yeah, I like that one actually. Yeah, software updates, that's a good one. There's not so software updates are the case where there isn't always a huge timeliness issue, although sometimes there can be if this is, Windows fixing another critical update or something like that. You don't necessarily want to be exposed to that vulnerability for a long period of time. That's a good one though. What's another one? Yeah, Natasha?
Virus scanning.
Yeah, there's a good one. Virus scanning, right? So that's something that's probably happening all the time on some of your machines. And yet you hopefully don't know about it, right? Unless it finds something, in which case you need to know, right? What else? Yeah. Yeah, that's one of my favorite examples, right? So, if you use a Mac, how many people use like Spotlight? Does anyone use Windows and use that dog thing? Is he still there? The dog? Yeah, what do they have now? Is it like just a search box? They got rid of the dog? The dog was cute. Yeah, that's the dog was back in this one. That was where the dog was, right?
Later implementations, but the Windows searching actually used to make the files it was indexing inaccessible when they were being indexed. So if you had, like with iTunes, if you were playing music,
it would just vanish?
You could not play certain songs if Windows was indexing them, so you had to disable it.
Nice. So Windows indexing for the win, right? While I'm indexing your files, I'll make them vanish, right? And then I'll put them back. It's like, thank you, Windows Indexer. Thank you for giving me my files back. Doing backup is another one. How many people have backups configured on their machines? How many? Okay, everybody raise their hand. This is a number of people who should have backups configured on their machines. Right? File indexing, examples of things that can be happening. And really, with these tasks, there are two main objectives, right? We want them to finish sometime, but we also normally don't want them to interfere with interactive use, right? We don't want the system to become unresponsive because it's indexing files. This can happen, right? But it's not something that we want to happen, right? So, and a lot of applications, merge a bunch of these things together, right? And use all of these types of features, right? So the music player clearly has an interface where interactivity is important. It has this continuity requirement for the music that's actually going to stream. And something like updating the album artwork or scanning for new files in your folders or whatever are things that are done in the background and need to complete but don't necessarily need to complete immediately, right? Web browser, obviously also has a UI. Lots of sort of media is now delivered through the browser. And when you're doing things like indexing your search history or syncing, if you have one of these sync clients set up or whatever, these are things that can happen more slowly, right? And to some degree, the mixture of these type of expectations is the very thing that makes scheduling really interesting, right? And makes scheduling sort of requirements sort of conflicting. So, imagine, and one of the sort of really difficult things for your computer to do is balance between trying to get everything sort of in use all at once, and then also at the same time being ready for this unpredictable, mercurial person who keeps showing up and clicking on things and expecting stuff to work, right? Like namely you, the user, you know? So imagine your machine's like, okay, right? So I've been meaning to do that, that backup, and I'm going to get that started, right? Because, you know, it's been a few hours and nobody has, you know, no one's been using me, and this is a good time to do it. And pretty soon the disk is going full force, and the networking, you know, stack is really busy. You're sending everything over to your, you know, remote machine, and then suddenly you walk up and like start typing in your password, right? And all the work the system's done to sort of get all these resources optimally allocated, it now has to sort of stop everything and try to respond to you. And this happens on a smaller granularity sort of constantly, right? I mean, you are the biggest source of unpredictability and irritation for the scheduler to deal with, right? If you weren't around, its life would be very easy, right? And responsiveness and continuity require meeting these kind of these deadlines that can either just sort of emerge out of the blue, like when you click on something, or continuity. What's interesting is that I have these predictable deadlines, right? And a lot of systems incorporate scheduling. It has some way for tasks to express these to the kernel, right? So if I'm the audio task, I can tell the kernel, you know, I kind of need to, I'm not going to take a lot of your time, but I really need to run every couple of microseconds, right? Because there's this buffer that I'm trying to keep up to date, you know, blah, blah, blah. So continuity has these predictable deadlines. Responsiveness has these unpredictable, and suddenly you click on something. And throughput, so throughput is the process of trying to make sure that when there is work to do, as much work is getting done as possible, right? And throughput, you know, again, is sort of really, really conflicts with interactivity, right? One of the things that we'll talk about, or you'll hear about in Friday's lecture, when we look at sort of measuring, how many people feel like they could measure interactivity? Anyone? How many people feel like they could measure the throughput of their system? Yeah, probably throughput might be a little bit easier, right? Interactivity is this weird thing. It's like you can, you know, what was the famous quote from the Supreme Court Justice about, you know, illicit content? He said, you know, I know it when I see it, right? That's kind of like interactivity. Like, you know when the system's not responsive, but it's not necessarily easy to measure. And the fact that throughput is easier to measure, and throughput is also important to a whole category of people who deploy operating systems and implement operating systems who don't use them on their, you know, operating systems that don't run on your personal machine. Throughput matters a lot more for certain types of server applications. These guys, you know, have been coming out ahead in many ways because interactivity is harder to measure, and also maybe not as important to the server guys who were driving the conversation about scheduling. So that's just a little preview of what you guys will hear about on Friday, right? And as humans, you know, we tend to prefer responsiveness and continuity. You know, you notice when the system stops being interactive. You notice when the video starts to get hiccupy. You don't necessarily notice how long the backup took, right? Whether it took 4 hours or 6 hours. You know, as long as it happened, you're cool. And part of the reason for that is, you know, poor responsiveness or continuity wastes your time, but poor throughput just wastes the computer time, right? And again, yeah, I've never heard anyone saying this, right? Like, my computer is not using all of its RAM, right? Actually, Linux geeks do start to say things like this. I have to run top, and it's like, what is all this unallocated memory? Like, I don't get it. OK. So now, when we start thinking about actual ways of making this decision, we come down to these sort of, again, conflicting requirements, right? So the first one is, how well does it meet deadlines, both these predictable continuity and these unpredictable deadlines? And then, how completely does it allocate system resources, right? When there is work to do, how effectively does it take all, you know, scheduled tasks to keep all the parts of the system busy that are needed, right? And again, this is, you know, the classic reason that interactivity wins. Your time's more important than your computer's, right? I'm not going to go through this aside. All right, so any questions about what scheduling is trying to accomplish before we go on? OK, cool. So we'll get through, I think, today a group of the simplest kind of schedulers, right? let's see here, right? So schedulers typically have 3 forms of information that they try to collect or predict in order to make decisions about which thread to choose, right? Without any information, there are some things that you can do, and we'll talk about a few of those schedulers today. But better schedulers, like the ones you'll hear about on Wednesday, usually use other types of information, right? One thing schedulers will try to do, and this is something we'll come back to over and over again, is they'll try to predict the future, right? What is about to happen? Because that's difficult, if not impossible, right? If you think it's difficult, you should go out and try it. A lot of times, what schedulers will do is actually use what just happened as an indicator of what's about to happen. And this is something that we'll come back to over and over again when we do VM. Use the past to predict the future, right? That's an OS mantra. And it's usually use the recent past to predict the recent future, right? If I go too far back, then maybe it's not as good a predictor. And then the third thing is most schedulers have ways for the system to layer on priorities and other outside information about what users actually want, right? And a lot of times, this information didn't even come from you. It's baked into your system, right? Windows knows that the file indexer is less important than a lot of other types of applications that are running, and so that information is communicated, when that process is run, right? You don't have to know that. Someone who designed your system software knows that, and they make sure that the operating system also finds out about it, right? All right, so so the first group of schedulers we'll talk about, however, don't use any of this information, right? And these schedulers have a couple of benefits, right? One is that they're really easy to implement, and the other thing that we use them for is as benchmarks to compare some of your other schedulers to. Because scheduling is one of these interesting problems where a lot of times people think that they can do really clever things, right? They'll be like, oh man, I had this example of this awesome scheduling algorithm. It's going to use like the time of day combined with like the lunar calendar, and I'm going to build up this really complex AI-driven model of the user behavior. And then you're like, actually, you just got outperformed by random, right? So your scheduler, not that effective. So this is the easiest one to implement. So this is an example of the simplest thing you could do. So without any other information, right? Let's say I blindfold you, and I say, you are the thread scheduler of your system. What is the simplest thing you can do that requires no extra information? I can pick a thread at random, right? All I do is I just twirl around and I point to someone and say, you, okay, you're running. It's your turn. And what I do is I pick a thread at random. I start the thread, and then what do I do? How long do I let the thread run? Till it's finished? Wow. I want you as my thread scheduler. That's one thing, but let's say I wanted to do a little bit more. Or what else could happen? Until the time runner fires, or what? Something else happens that causes this thread to block and not be able to continue, right? So I start T3, and let's say T3 runs through its quantum, and now I need to schedule somebody else. So what do? Pick someone else at random, right? I put now T3 has finished, right? He didn't block. He, she, I don't know. It didn't block. It's a man. It wouldn't shut up. Finished its quantum. Anyway, sorry. I shouldn't make gender jokes about the threads. They don't like it. So now I pick someone else at random, right? T5. And in this case, let's say T5 runs, and it actually makes a blocking system call. So where does T5 go? So T5 goes onto the waiting queue, but now I have to make a scheduling decision, right? Who do I pick now? Who knows? Let's pick T2, right? Put up T2. T2 finishes quantum. Where does T2 go? Ready. Onto the ready queue. Right? Still runnable. Now what do I do? Who do I pick now? Who cares? T4 doesn't block. Sorry, T4 blocks. T4's out of the waiting queue. And I continue this, until the end of the slide, the edge of time. And this is the simplest, most basic example of thread scheduling. But again, if your scheduler can't outperform random, And I would encourage you guys to do this for assignment 2. Implement a, I don't know, even just, I don't know what you could do, some sort of smart scheduler, right? And then see if you can beat random, right? Because random has an advantage. Random has very low overhead, right? Random doesn't do a lot of thinking about what to do next, right? Random just, whatever. I just got some dice here, I'm just going to throw them, and that's how it's going to work, right? All right, so this is random scheduling, okay? And what we just did, right, and this is common to how you design scheduling algorithms, we chose a scheduling quantum, okay? A scheduling quantum represents the longest period of time that I'm going to let a thread run before preempting it. And fancier schedulers don't always have one scheduling quantum. Sometimes they have one quantum per priority, and they do some fancy things. But anyway, you can think of it as just having one quantum, right? That's the longest I will allow a thread to run interrupted before I will preempt it, right? And then, I choose a thread at random. I run the thread until it blocks. Now, what happens when a thread leaves the waiting state? Let's say a thread was blocked on I/O, and that I/O finished, and now the thread can continue. What do I do? Anyone remember? I just throw it back in the ready pile, And this isn't, you shouldn't call it a queue, right? Because I'm picking from it at random. So it's a pile, not a queue. A queue has an order. So let's try, moving on from piles to queues, right? And I would say, actually, I think random is simpler, but this might be conceptually a little bit simpler. What do you think round robin scheduling does? Yeah, so first thing I need is, now I actually need a queue, right? I need something with a front and an end that maintains an order, okay? And when threads are created, I could put them in the front, I could put them in the back, who cares? Doesn't really matter. At some point, they're going to get the chance to run. And now all I do is I pop the thread off the head of the queue. I run it till it blocks, or until its scheduling quantum expires. If its scheduling quantum is expired, I put it back at the tail of the queue. Otherwise, it's on, where is it if its quantum hasn't expired? It's on the waiting, it's in the waiting state, right? When a thread leaves the waiting state, what do I do with it then? I could put it at the head or the tail. I just need to get it back on the queue. There's, round robin schedulers don't try to maintain a global order over all threads, right? They're very flexible. They're just going in round and round the group of threads that are actually ready to run, right? And these schedulers, we collectively maybe call them the KnowNothing schedulers, right? These schedulers don't take any user input. They don't try to collect any statistics about what the threads are doing. They don't care, right? These are very simple schedulers. And the only real reason that we ever use these schedulers or talk about them is, again, as straw men to compare your other fancier schedulers to. All right? And this is an interesting thing to note, right? So one thing you guys will hear about on Wednesday is one thing I might want to do is reward threads, or at least handle threads differently, or at least notice when a thread blocks before its quantum expires. Why is that? Why would this be an interesting piece of data for a scheduler to collect?
Increased chances to reschedule?
Well, the thread has given me the rest of the quantum to use for something else. But when we go back to those three sort of types of tasks that the computers might be performing, yeah. Well, maybe. Yeah. What's that? Yeah, well, OK. Well, let's go back. So there was the interactive tasks. There were the sort of continuous tasks. So the interactive tasks respond to user input and do something. The continuous tasks usually, do repeatedly something sort of fairly often. And these throughput-based tasks have long amounts of stuff that they need to do, right? So which one of in that group is the most likely to block quickly? It's a hard question to answer, I'll admit. So keep in mind, scheduling quantums are usually pretty long, right? I mean, I know they don't look long on this sort of dinky slide, right? But whatever. I mean, I guess I can define the axis to be whatever I want to because it doesn't have one. So imagine this is like millions and millions of instructions, right? It's just a long period of time. So if I'm an interactive task, let's say I'm your shell, right? What does your shell spend a lot of time doing? For what? You hit a character, right? Then when you hit a character, what does it do? Prints the character on the screen. How long do you think that takes?
Not very long.
Not very long. So there are schedulers, and it's not, you know, and we'll come back to this. This is the sort of a hot debate about, so one of the things that schedulers will frequently try to do is detect interactive behavior, right? So again, going back to our computer human expectations, why would I want to detect interactive behavior? Why would it be really useful for the scheduler to know which tasks are these interactive tasks and which tasks, say, are the background tasks? Yeah?
So we can give priority to interactive tasks because they are the tasks which gives user feedback.
Yeah, so when an interactive task, so think about it, the background task, no one cares about the background task, right? Again, no one is sitting there being like, you know, 3 hours and 42 minutes and my backup is still running, you know, 3 hours and 43 minutes and like, does anyone do that? I don't know, I don't do that. I'm assuming you guys don't do that because you have better things to do, right? So these background tasks can be delayed if they need to be. But once you hit the key, the clock starts ticking, right? And your expectation timer is going to fire. So as soon, yeah, so, and prioritize is a tricky word, and we'll have to come back to what that means in the context of scheduling, particularly when we look at schedulers that try to prioritize quote unquote interactive tasks. But certainly, if I can recognize that a task has an interactive nature to it, when it's ready to run, I can say, you know what? Someone is probably waiting for something to happen. An actual human being out there is probably looking at me right now and being like, are you going to draw the key? You know, I just pressed an H. Is an H going to appear on the screen? Whereas with the non-interactive tasks, again, like if I stop them for 10 minutes, no one notices, right? So interactivity detection is something that we'll come back to, but it's something that a lot of schedulers try to do, and it's not an easy thing, right? Yeah?
Why do we need to detect interactivity? I mean, we know which processes are interactive, right? Beforehand?
Not necessarily. No, I mean, schedulers wish they knew that stuff, right? And you can take some hints, right? But remember, even most apps, right? Nowadays apps will have a lot of threads. Some of the threads may be interactive, some may not, right? Apps go through phases where they're in an interactive phase and they're in more of another kind of phase. So yeah, I mean, it would be awesome if you could just label your threads in this way. What would be the problem with doing that? Yeah. Yeah. I have a great idea for how you can produce the world's fastest virus scanner, right? Just label all your threads as interactive, and then off they go, right? And then the computer's not going to be very interactive once you get going. But the point is that, you know, yeah, it's too easy. So I need to use, you know, schedulers usually try to detect this rather than either trust threads to tell me or do these sort of out-of-band approaches like looking at process names, right? All right, so on Wednesday is Bring Your Design to Class Day. So again, you know, please come to class on Wednesday. I think it'll be really helpful. Bring whatever you have. If it's half a page of, you know, written notes or whatever, bring it to class, and you guys will get some feedback from other groups. So enjoy the rest of the week. I'll see you next Monday.